So, today we're going to be talking about topic 1.7 and topic 1.8 because they go hand in hand. Right. So, topic 1.7, 1.8. And then next after this we're going to do 1.9 and 2.0. And then once we're done with those two, we're going to do one central video on just everything about rational functions. But this is just a kind of small video just to do a little recap. But I'll have a full rational functions video before the test, so look forward to that. So, we have lots of different types of rational function. Okay, so I have 3 examples here of different rational functions. And now a rational function is just one function divided by another function. Very simple. So, with all of these functions, they all have different rules and properties about them. So let's check this first one first. So we have 2 over x plus 3. Now, to understand this, let's think about this in terms of graph, right? So let's say x is equal to 0, so our y-intercept is 2 over 3. So we're right here. What's going to happen as x goes up? Well, 2 is going to be divided by greater and greater numbers. So 2 over 4, that's 1/2. 2 over 5, that's 2 over 5. And 2 over 6, 2 over 7, 2 over 8, 2 over 9. But you never, never, never go to 0. You always just get super close to this line. You're going to have, like, I don't know, 2 over 1 million billion trillion, right? But you're never below 0 because you can't divide 2 by something that would get you 0. It doesn't make sense. Which means that if what's on the denominator has a greater degree than what's on the numerator, then that means the denominator will increase as x goes on faster than the numerator will. You can see this in an example right here as well, right? Even though we have x in both, the x up here is superior. It's like an arms race. Who's going to win? The x up here. So that means the intercept isn't 0 because it's not going to divide infinitely. But here, the x on the bottom wins because the x down here is superior. And when you're dividing by 2 over 1 million 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 billion plus 3, you're going to be really close to 0. But now we're touching it. So, greater degree on the bottom. If the x on the bottom wins the arms race, then that means that it endlessly approaches 0, but never touches it. Now let's look at this example right here. In this example, the top x wins the arms race, right? So, they're not equal. The x up here is a square, and this x down here is just 1. So what ends up happening is we have x going like we're winning, right? We win, we win, we win, we win, we win. And then x is increasing exponentially. But what's interesting about x being higher on the top is that you actually have a slant intercept. And what I mean by this is better explained if I look at this. And, you know, for the sake of the example, I'm just going to change this to square. Now, if we have both of these being the same, then that means they're kind of equaled out, right? And if we have them equaled out, then that means the horizontal intercept, this line right here, is the ratio of the 2 highest degrees, the coefficients. So if we have x squared, then 2 over 1 is 2. So then the y would be 2 for this line. Let me make this different color. Y would be 2. And then you would just have your lines going as normal. We aren't going to really cover finding out where the y-intercept is, where the hole is. We're not going to do that yet. That's the next unit. But for now, what's really important is that we know where this function is. which is where we get into 1.8. But quick little recap before we do that. So, X on the bottom wins. It's like a tug of war. The X on the bottom has more manpower, and that means you're always approaching X because you're dividing by a bigger and bigger number. The X on the top wins. You end up with a slant intercept, which is really interesting. It looks a little bit like this, and then you have a slant intercept, and then your lines look like that, and then they look like that. Really, really interesting. Not sure why it works, but that's just how it is. And also, if you want to calculate the slope of this line, what you're going to do is use this handy little formula. So your slope of this line will be, let's see, so if we have two functions, the top 2 degrees are what matters. Like the highest degree of both functions are what matter. So we're going to have the coefficient of 1. So let's actually model this out. So we have a over b and then x, y. Right? So this one is going to have the higher degree. This is a higher degree because it's on top, and then this is a lower degree because it's on the bottom. And this is only for this specific situation to find the slant intercept. Right? And then these are the respective intercepts. So to find our line, all we have to do is do a over b x to the x minus y. Now I should probably change this variable so you don't get confused. Z. There we go. So y equals a over b x to the power of z minus y. Essentially what you're doing is you're doing the same thing as over here, except you're just making it a line and then making the line's exponent be these two. This is 1, so these two. Right? So a over b, 1 over 3, that's just 3x, and then z minus y, 2 minus 1, that's just 1, equals y. So our slope for this line will be 3x. So we'll have our thing here, and our asymptote will look like this. Line 3x, and then we'll have our lines. I don't know exactly how they look, but they're going to look like that, somewhat like that. And they're going to follow this line. Easy peasy. So just divide the coefficients and subtract the exponents. It's just the same thing you're doing over here, really. You could just do the same formula, where you have, actually you could do the same formula to all of these, really. It's the same kind of logic. So if you do it here, if you have 0 over, doesn't even matter what we put on the bottom, but 1 to x to the power of, doesn't even matter really, 0 minus 1, because whatever the case is, 0 divided by anything is 0, times 0 to the power of whatever, it doesn't matter, it's 0. So our y is going to equal to 0, and that checks out, because we have a line that looks like this, always approaches 0, right? And then if we use this formula over here, let's say 2 over 1x, I'm taking these, and then 2 minus 2. So that's 2 over 1, x to the 0, which is just 1, which is just 2. So your horizontal would just be y equals 2. So this formula actually works on all three. However, it's not really necessary once you see the patterns. It's just something to have to help you remember. So, final recap. When x is bigger on the bottom, division, it keeps dividing and getting bigger and bigger and bigger. When x is higher on the top, then that means that there is a slope as a asymptote, and you can use this formula here to find it. So you just do the coefficient over the other coefficient, and then the exponent minus the other exponent. Now here we're just going to do the coefficient over the coefficient, because the exponents just cancel each other out, so there is no x. But if you're ever not sure, just use the formula on any of these and it will work. So it's a over b x to the power of z minus y. Now, what we are going to move into is factoring rational functions and inequalities with rational functions. Now, you've already learned about factoring and you've already learned about inequalities with polynomials. So the only thing I am going to teach you about this is that there's one extra step, right? So we have x minus 2 over x plus 6, x minus 3. In this situation, we'll greater than or equal to 0. And then we'll do a second one where it's greater than 0. We just delete this. Okay, situation 1, right? So we just factor as normal, right? We have all our zeros here. Draw our sign chart. And then, okay, we have negative 6, 2, 3. We plug in a test value for this first initial point. So let's say negative 10. So negative 10 minus 2, negative. Negative 10 minus 6, negative. Minus 3, negative. So it will all be negative. Negative times negative is positive. Negative over a positive is negative. So we start negative. Cool. So I'm going to be using the method that I have a video on. Just look up sign charts the easy way. I should have it updated by today, but that will tell you how I'm doing all this magic, silly, funny business. But if we start from negative, take a look at this. Odd exponent, flip. Odd exponent, flip. Odd exponent, flip. Very simple, easy, right? So we need to find what's greater than or equal to 0. Easy. So we're going to say what's greater than or equal to 0. Well, this is positive, so we're going to do like that, and then we're going to do like that, except we're not going to do that. And you ask yourself, why? Why aren't we doing that? Well, the problem here is this negative 6. Because if we were to take this bracket seriously and say, okay, what if our x is equal to negative 6? Then this would become 0. Let me get my pen. Where is it? This would become 0, and then 0 times anything is 0. You can't divide a number by 0. Anything above 0, that doesn't work. You can't do that. That would be undefined. Which means that this bracket actually has to be a parenthesis. And the way that you know how to do that easily is just anything on the denominator, you don't count the 0. So negative 6 is on the denominator, so we don't count the 0, we put a parenthesis. Negative 3, or positive 3 right here. Normally we would put a bracket and then 3, not here, because it's on the denominator. So we're going to put 3 comma infinity. And note this 2, we bracket it because it's on the numerator. If we were to make that 2 0, 0 divided by anything is just 0. That just makes sense, that works. It's not the same as if you divide something by 0, right? So any zeros on the denominator, you want to make sure to put parentheses on them, so that way you don't get an undefined answer. And another edge case here is if you were to have, let's say, I don't know what equation it is, but let's just say you have 0, and then you have minus, and you have minus, and then you have to be greater than or equal to 0, right? You may think, oh, greater than or equal to 0, we have a 0 right here, and really this could be any number, it doesn't have to be 0. It could be like 10, I don't know, doesn't matter. It's just an x point where it dips through the y-axis. So you may say, oh, this is or equal to, and this is equal to 0. And you're right. Except if that 10 is on the denominator. In that case, you can't do that. And then you'd have to say undefined. Oh no. She wants you to put never. Because essentially it's asking you when is this true? And you're saying, oh, it's never true. So that's one edge case you need to know, because it's probably going to be on the test. Right? Let's go to the second situation here, right? Where we are just greater than 0. We're going to do the same thing as before. We're going to go -6, 2, 3, and then we already know that we start negative because we did that work before. And then really we just copy this. So we already did it. Greater than 0. Well, now we just put parentheses on everything. And that works. That's okay. The real finicky business is when you have those brackets involved, is because you need to keep an eye out for that denominator. Anything else I need to cover here? Right, factoring. Factoring is interesting. So we have, let's say, x squared minus 4 over x squared plus 1 equals greater than 0. Throw a sign chart, right? Oh wait, we need to factor it, sorry. So we're going to factor this. We're going to say, okay, x squared minus 4, well, difference of squares. We're going to do x minus 2, x plus 2. Easy peasy. Now here, you can't really factor that, and it's not in the right form. If you were to factor this, you would get x squared plus 1 equals 0. Minus 1, minus 1, x squared equals -1, square root of -1, which is just x equals plus minus I. What do we do? My favorite thing. Ignore it entirely. Just pretend it doesn't exist. If it's an imaginary number and you can't do anything with it, guess that sucks. Just don't touch it. Just don't worry about it. You got your 2 zeros over I don't care. Smiley face. And you just do your sign chart as usual. So, -2, 2, greater than 0. We plug in 2 test values. Oh, here's... Actually, it still doesn't matter. Because that is always going to be positive. No matter what. And you can't put in 0. Well, you can. But that's always going to be positive because it's plus 1. So just assume this bottom one's positive. Because here, let me erase these. Here. No matter what value you put in, even if it's 0, this will always be positive because it's added to 1. So just this is always positive. So positive, I don't care. So if we do -4 as our test value, -4 minus 2, -4 plus 2, negative, that's positive, positive over positive, we start positive. And then these are odd coefficients, we just flip. Greater than 0, we would do, remember, no greater than or equal to. So, -infinity, -2, to infinity. To infinity and beyond. That's pretty much all there is to it, or at least all there is that we've learned for now. I will do more work on vertical asymptotes and holes in the next video, and then before the test I will make a full rational functions video. But I hope this helped, and I hope you enjoyed.